Hello everyone. Today we'll study the how to do the 4-bit array multiplication. Okay. For this purpose we need to have two data. One is the multiplicand. Here the multiplicand I have initialized it as B and the multiplier I have initialized it as A. The data I have taken is 1011 and the second number is 1110. The logic in designing this one is, what we basically do is we'll multiply every bit of the multiplicand by the multiplier bit. Now can you see that one? The first bit of the multiplier is 0. Now the first step is we'll multiply this 0th bit with all the bits of the multiplicands. That will give you 0 into 1 is 0, again 0 into 1 is 0, 0 into 0 is 0 and 0 into 1 is 0. This is the first step. Now when it comes to the second step, what we do, we'll take the second bit of the multiplier. Again we'll multiply all the bits of the multiplicand with this multiplier bit. Okay, that will give you 1 into 1 is 1, 1 into 1 is 1, 1 into 0 is 0, 1 into 1 is 1. But we do, in the second step we don't only do the bit multiplication, we also shift the data one position to the left. Okay, this x indicates it's a don't care operation, but we basically append it with 0. Okay, now the third step is we'll again take the third bit of the multiplier and we multiply every bit of the multiplicand with the third bit of the multiplier. That will give you the result 1011. But in the third step we shift two positions to the left and we append zeros. Okay, similarly with the last step is we'll multiply the fourth bit of the multiplier with all the bits of the multiplicand. That again leads the result 1011, but here we shift 3 positions to the left. Okay, and we append the LSB 3 bits to 0. After all the multiplication process, we finally need to add the result. Okay, this will give you 0 plus 0, x indicates 0, 0 plus 0 is 0, 0 plus 0 is 0, 0 plus 0 is 0, that will give you the addition 0. Similarly, when it comes to the next position, it is 0 plus 1, 0 plus 1 is 1, 1 plus 0 is 0, 1 plus 0 is 0, so that will give you 1 with a carry of 0, again 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 1 is 0 with a carry 1, again 1 plus 0 plus 0 is 0 with a carry 1. Similarly, it goes 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 1 is 0 with a carry 1, 1 plus 1 is 1 with a carry 1. Okay, then it comes 1 plus 1, 0 with a carry 1, 0 plus 0, 0 with a carry 1, 0 plus 1 is 1 with a carry 1. That will give you 1 plus 1 is 0, 0 plus 0 is 0 with a carry 1, 1 plus 1 is again 0 with a carry 1. This is the final result we have to do. This is what the logic we need to follow to write a program. Now let's see how we have written the program. Okay, this is the Verilog code we have written. We have started with the module. We have initialized. You can see from the logic we are giving 2 inputs and we are getting one single output, and whatever the stages we are performing in between these input and output, those are the intermediate stages, but actual input we are giving only A and B and we have to get the final output. Okay, now so that's why we initialized A comma B comma P. A and B indicates the input and P is the output. Okay, product output. Now input we are doing a 4-bit multiplication, so that's why I have taken input 3 down to 0. That indicates both A and B, that is the multiplicand and the multiplier, are 4 bits. Now I have initialized the intermediate stages as wire. Okay, so what we have done, you can see from this logic, the first multiplication what we did, we got a 4-bit. The second multiplication, the second stage, we got it is 5-bit. The third one it is a 6-bit and the fourth one is a 7-bit. So that's why we have initialized it. We have named it as M0, M1, M2 and M3. The same thing we have written in the Verilog code also. You can see here the first stage we got only a 4-bit output. In the second stage we get a 5-bit output because we shifted one position to the left, and in the third stage we'll get a 6-bit output because we have shifted 2 positions to the left, and in the last stage we got a 7-bit output because we have shifted 3 positions to the left. So I have initialized all these intermediate stages also, and output we have all initialized output 7 down to 0 P. That indicates the when you are doing in a 4x4 multiplication, the maximum output you can get is 8-bit. So that's why we have taken the maximum data, that is 7 down to 0, that is 8-bit data. Now we need to do the operation, the first stage operation. What is the first stage operation we are basically doing? you can see from this logic, we are taken the first LSB bit of the multiplier, and then we are multiplying all the bits of the multiplicand with this multiplier. The same thing we have written here. What we are doing, basically the multiplication indicates an AND operation, right? So that's why we are taken A of 0 means that is the first LSB bit of the multiplier, and we are doing the AND operation with all the bits of the multiplicand. That will give you M0. Similarly, we'll take the second bit of the multiplier and we are doing the AND operation with all the bits of the multiplicand. That will give you M1, similarly M2 and M3. Now, if you can see here, M0, M1, M2 and M3, what we got, these are all not shifted versions. If you can see here, M0 indicates 0, 0, 0. M1 indicates 1, 0, 1, 1. M2 indicates 1, 0, 1, 1. M3 indicates 1011. Okay, that is what we got. We haven't got the shifted positions. Okay, so here that is what the result we got. Now we need to add every column, right? So that's why we are taken assign S1. These are the S1, S2 and these are intermediate stages. This is supposed to be S3, sorry. This is supposed to be S3. S1 is equal to what we are taken, M0 plus M1 shifted to one position to the left. Okay, M0 is basically, you can see from this logic, M0 is not a shifted version. This is we are directly taken. But what about M1? Whatever the result we got, we shifted to the left by one bit. So that's why here also we can write M0 plus M1 shifted to one position to the left. Okay, that will give you the S1 will give you the addition of this first row and the second row. Fine. Now addition of first row and second row will go to the third row addition. Okay, so that's why we taken assign S2 is equal to S1 plus M2 left shifted 2 position, because M2 whatever we got from this line, this is unshifted, this is not at all shifted, this is just a AND operation. Okay, but what is our procedure? We need to shift it 2 positions to the left, so that's why we shifted this one, then we did the addition from the previous one. Okay, this will give you S2. Similarly, this has to be S3, sorry. So assign S3 is equal to S2 plus M3 shifted 3 position. You can see here, this is M3. I am shifting it to 3 positions to the left, and all the 3 additions of M0, M1 and M2, it will be stored in where? It is stored in S2. So S2 plus M3 shifted 3 positions will give you S3. Okay, and S3 is the final product, so that's why I am assigning it to P. Okay, this is the logic of the program. This is how the 4-bit array multiplier works. Thank you.